So I'm audible, right? And also my slide are visible.
Yes, sir.
Okay, thank you.
Yes, sir.
Okay, so today we'll be again discussing on this little bit some question on vector spaces which we left for the assignment 2, that was in assignment 2. So we'll discuss some of them, and then when we'll go to this system of linear equations. So just a brief recall of this vector space, what it is. So again, so vector space is first you have a field K. K is a field, and on a space non-empty set V there is a operation, binary operation plus, so that this V plus is a abelian group. And there is also another operation dot, which is from K cross V to V, which satisfies 4 conditions. First one is again, it is in the K there is multiplication, say, so I can have multiply first this, take A dot B, and then with this, and this should be same as AB, use the multiplication in the field K, and then dot with V. Then again you have addition in the field K, so I can take A plus B. This plus is the plus of the field K, and then take dot with V, that is same as I take A dotted with V and B dotted with V. Third one is in the this V also you have plus, so there I can take any A V plus W, so this is A dot V plus A dot W. And the third one, there is one element, identity element 1 with respect to the multiplication in the field K, so there is 1 dot any V, that is V. So all these thing happens for all A B belongs to K and V W belongs to my this set V. Okay, so then this will be a little bit huge, and the subspace thing, recall again that subspace. So you said a subset W of a vector space V if two conditions are satisfied, that this W is closed under this V, that means it is a subgroup of this V plus W, and also this dot thing is satisfied. So basically if you combining both of them, then you will, if A dot V plus B dot W, this belongs to always this W for all A comma B belongs to K and VW belongs to W. If VW belongs to W, then you must have this, then you said this W plus dot with the induced plus dot of V is a subspace. And then we'll see for the system of linear equation, that you have a system of linear equation. So system of linear equation, so equation, so in a vector space V, you can write a system of linear equation. For example, this Ax equal to B, this is a system of linear equation. We say this A belongs to matrices M cross N matrices whose entries are from this field on which your vector space is. So V, and X belongs to your vector space X and B, so B comma X belongs to your vector space V over the field K. Okay, so this is basically a k power, so v is, in this case actually it is a k power n. Okay, so then we say this is a ax equal to b, this is a linear system of equation which this x we want to find, given a and b we want to find this x such that this equation ax equal to b, this is like a matrix equation, so this is satisfied. This has either this has solution or it may not have solution depending on the homogeneous system. You have seen that you consider this ax equal to b, this homogeneous system. If this system has solution, then we take a particular solution of this ax equal to b, and that has a solution. So if this ax equal to 0 has only 0 solution, then this system has unique solution. Otherwise, if ax equal to 0 has no solution, then we say that this ax equal to b also has no solution. Okay, so that's all for today. That we'll be discussing more mainly on these ideas. So let's go to the first question. And so this says that if you have a vector space V over a field K, and X is any set which is in bijection with this vector space V, then this question actually shows that you can actually induce on the set X a vector space structure defined through this relation. Because first of all, we want this on X, I want to give a plus operation and dot operation such that this with respect to this plus, so it forms a abelian group, and with respect to dot, the four conditions satisfied. Okay, so is this question clear to everyone? Okay, so let me go through it. So first you have this map A from X to V, and this is just a bijection, and on V I know, so this plus actually you should whenever I say this fx plus fy, this plus is the plus of this V being a vector space. So there is plus, so this plus is referred to the plus of this vector space V, and this whenever I don't make any dot or this thing, this thing is the scalar multiplication defined on the vector space V. Okay, so here this A belongs to K, X, Y belongs to X. So first of all, I want to check that this X with this plus is a forms an abelian, right? Okay, so first of all, this is well defined. This plus from X cross X to X, this is well defined, because if I take two element X and Y, and X comma Y, this I am sending it to this F inverse of Fx plus Fy. Okay, because this is a bijection, so I'm just mapping the X and Y to V, and there I have the addition, so I'm adding them there, and then again taking the inverse, so it again lands on X. So this is first of all well defined. Then first of all, this is associative. Okay, so associative associative because again this plus is associative, because if I take X plus three elements X, Y, Z belongs to, okay, so X, Y, Z belongs to say X, then I first make X plus Y, then with Z, so this is by definition F inverse of, this is by definition that F of F inverse of F of X plus Y plus, so F of X plus Y, and then or first I should first perform this plus, right? So F inverse of Fx plus Fy, this thing, and then plus with z. Then this is this plus again by definition of this plus. So again I have f inverse of f of this thing, which is just fx plus fy, because f of f inverse of fx plus fy, f of f inverse, that is just identity, so this is just fx plus fy, and then f of z. So this I have, this is by definition, but in the bracket thing you have fx plus fy plus fz. So this plus plus is in the vector space V, so there this plus is associative, so I can write it is same as fx plus fy plus fz, right? So as V plus is associative. So again if I like come back in this thing I can write f of f inverse of fy plus fz. So that thing I can write as f inverse of, or so this I can write as x plus this plus is this plus on defined on x, and then f inverse of fy plus fz, right, as we did here, the same thing. Okay, but this by definition again is y plus z, so this is x plus y plus z. So this shows that this is true for any x, y, z belongs to x. So this proves the associativity of this plus defined on x. Okay, so now next we need to check that identity thing. So already in the question itself given that f inverse 0 is the 0 element, that means the identity element with respect to this plus. So just check that. So for any x belongs to x, I should get that x plus f inverse 0, this 0 is in the vector space V, so this is by definition f inverse of fx plus f of f inverse 0, that is just 0. So this is fx plus 0, 0 being the identity element in vector space V, so this is just fx, so f inverse of fx, and this is f inverse of fx is just x. So this is the identity element. Also like if this plus is commutative, so again like you can take this also. So this is again by definition this is 0 plus fx, which is f inverse of fx, which is x. So this implies that f inverse 0 is the identity element or 0 element. Okay, third is inverse. Inverse again you can guess from here that it is just the f inverse of minus x, right? So if I take x belongs to x, its inverse should be f inverse of minus x, right? So f inverse of minus x plus x, this is by definition f inverse of fx, and then it is f of f inverse minus x. Okay, so better I should write in that form. Okay, for each x belongs to, so I should write it in this form, that fx of minus x, that okay, so for each x you know that f inverse x or f inverse of minus x does not make sense. So x belongs to, so fx belongs to V, so it has the inverse minus of fx, right? So I should pull back that thing, so this is not the correct thing. I should pull back f inverse of minus fx, right? It makes sense because minus fx is in V. So I'm claiming that this is my inverse, and this is my inverse because by definition again, this by definition f inverse of fx plus f of f inverse of minus fx, so this is just minus fx. So here this minus fx plus fx, this thing is 0 there, okay, by definition of the inverse in V. So this is again f inverse of 0 because this is 0, and f inverse 0 0 is the identity, so this is this thing. Similarly we also get that this is same as x plus f inverse of minus fx. And next is the commutativity because the same thing, that x y belongs to x, then x plus y is by definition that f inverse of fx plus fy, and this plus is commutative on V, so I can again write it as fy plus fx, and this is again by the definition of plus on x, this is y plus x. So this is commutative, so each element has an inverse, so thus x with the defined plus is an abelian group. Okay, so this is abelian group part done. Now the multiplication on x is defined like a dot x equal to f inverse of a fx. So these should satisfy the 4 condition. So let us check that. So first one for scalar multiplication, a dot x equal to, this is by definition f inverse of a fx, right? So f inverse of a fx, a belongs to k and x belongs to v, x belongs to x, sorry. So first one again, like take a dot b dot x, ab belongs to k, so this is by definition a dot f inverse of b fx, but this is again by definition f inverse of a dot f of bfx, so this is just bfx, right? And this I can combine this ab both, so that because in the field you have already the scalar multiplication satisfy a b fx equal to a b fx, right? So this is just f inverse of a b fx, so this is again by by definition this is ab dot x, sorry, ab dot x. So this for ab belongs to k and x belongs to x. Similarly for the a plus b dot x, this is just again just the like using the plus operation in the v, because it is like satisfy there everything, so it is just using, so it is f inverse of a plus b fx, but this is there, so a dot fx I can take f inverse of a fx plus b fx, right? And on the other hand also you have a dot x plus b dot x. So this is by definition, first of all, f inverse of a fx plus, this plus is the plus in x, so be careful here. So this is not just the plus there. So this is again using the plus in x. This is by definition f inverse of f of this thing plus f of this thing, but f of this thing is a of x, so this is again same as a f x plus b f x. So these two are same. Okay, so this thing also done. Third is just taking x plus y, so a dot x plus y is by definition f inverse of a fx plus, or okay, so I should first perform this x plus y, so that this is a dot f inverse fx plus fy, and then this is f inverse of a dot f of this thing, so a into fx plus fy. Okay, so f inverse of this thing, but again this thing satisfied like above thing, like f inverse of a fx, because this plus is happening in your vector space V, so a fy. This again using this computation, you can see that this is a dot x plus a dot y, and 1 is like in this case 1 is still again the fourth thing. 1 dot x is by definition it is f inverse of 1 dot fx, but 1 dot fx is fx because this satisfied, so this is just not 1, it is just 1x fx, so this is f inverse of fx, which is just x. So all the four these four conditions also satisfied for the scalar multiplication, hence x plus dot, the plus as defined previously, so this is a vector space. Fine. So so the aim of this question, actually, whenever you have bijection from a vector space to any set, you can like pull the structure of push the structure of that vector space to that set. So whichever set you take, you can do that if you have the bijection with the vector space. Okay, so is this fine? Okay, so then let's go to the next one. So the next one is again related to the subspaces. So similar question we have done in the previous class, that if you have u prime w prime are vector space V over a field K, then this subset V minus u minus w, that means u minus w complement in the vector space V, is a subspace of V if and only if you either have u exactly equal to V or u contained in W. Okay, so do anyone have any idea how to proceed for this question? Or have tried this thing? Okay, then let's proceed. So this u and w are subspace, so I have to use somehow their property of u and w subspace. So first of all, this A, assume that this is a subspace, V minus u minus w is a subspace. So I need to show that this either of these conditions satisfied. Okay, so first suppose that u not equal to V. So then I should get that U must contain in W, right? Suppose U not equal to V. That means U is a proper subspace of V. So I can pick an element which does not belongs to U but belongs to V. So take X belongs to this V minus U. Okay. So that means it does not belongs to U but belongs to V because this is proper. So such X exists. Now take any. Now let Y belongs to Y belongs to U, because I want to show that U contain in W, right? So I should take, if I take any element from U, then I should say show that this Y belongs to also W. So let take Y from U. Then I have to somehow use the subspace. This is a subspace, so that this actually so that this Y belongs to W. Okay. Now taking X and Y, this one belongs to U complement, another belongs to U. So what can we say about X plus Y? That's the first thing we should ask. So then everything is happening in V, so X plus Y must belongs to V, and V I can write it as like disjoint union of U union V minus U, right? So it either belongs to U or V minus U, but they are like disjoint, so disjoint union. But if X plus Y belongs to U, then also and also Y belongs to U, and U is a subspace. So I get that from that X equal to X plus Y minus Y, that is valid in your valid element in your subspace U, so that belongs to U. But our choice, X does not belongs to U, so this must belongs to. So this implies X plus Y belongs to U, or X plus Y belongs to V minus U. But as U is a subspace and Y belongs to U, so X plus Y belongs to U implies that X equal to X plus Y minus Y belongs to U, which is not possible. It's not possible because by our choice X belongs to V minus U. Fine. So this implies X plus Y must belongs to V minus U. So X belongs to V minus U, and X plus Y also belongs to V minus U. And look here that this is V minus U minus Wj subspace. So now X plus Y, so this belongs to V minus U, that means also that this belongs to V minus U minus W, right? So X plus Y comma X belongs to V minus U minus W, right? Because this is this. So if I like write it in like in the union intersection form, so this is V minus U minus W. This is nothing but V intersection U minus W. So U minus any set minus that thing means that A minus B is A intersection B complement, right? So here also you have U minus W complement, but U minus W is again U intersection W complement whole complement. Now by De Morgan you know that U intersection W complement whole complement, that thing is same as U complement union. So this is V intersection with U complement union W, right? So every element belongs to V. So anyway U and this U and W all are subspace of V. So this intersection is nothing but just U complement union W. So this is this, and I take my V minus U. So this is belongs to X belongs to U complement, and also in this case also X plus Y belongs to U complement, right? So this is just U complement and this is U complement. So this implies that X plus Y comma X both belongs to this V minus U minus W, that is just U complement union W, right? Because this is belongs to U complement itself and belongs to this, and V minus U minus W is a subspace. So this is a subspace, so I can like subtract them, just that like add the inverse of this thing. So Y, that is just X plus Y minus X. So this belongs to this V minus U minus W. But this Y I took from U, so it does not belongs to U complement, and this is just the union of this U complement into union W. So this element belongs to this union, so it belongs to either of them, but it does not belongs to U complement because this belongs to already U by assumption, so it must belongs to W. So this implies that Y belongs to W, as Y belongs to U, that is Y does not belongs to U complement. Okay, so we picked Y from U and stored it in W, so we must have U contained in W. So this implies U contained in W. So this I assume that U not equal to V and stored that U contained in W. So if I assume the other thing, that if U not contained in W, then I should say that U must be equal to V. But again, like if U not contained in W, or okay, so U not contained in W, the other case, suppose U not contained in W, if U not equal to V, like assuming both the thing, first suppose this, now if U not equal to V happens, then by previous case, then we knew that then we must have U contained in W, which is not the case here. So we must have U equal to V. By previous case, right? So hence U must be equal to V. Okay, so this take care for the forward part, that if we assume that this is subspace, then either of these happens. Now what happens in the like reverse case, that is easy, because if U equal to V or U contained in W, in this case if U equal to V, then what is this thing, V minus U minus W. So U already deleted, so V minus U minus W, that thing is just, so V minus, so this is V minus U minus W is U complement union W, right? But U complement is just is phi, because this I am taking the complement in V itself, so this is just W, so which is a subspace. So let me write it in there. below thing, that this is just V, so V intersection U complement union W, but U complement is phi, so this is just V intersection W, which is W as U complement equal to phi. Okay, so which is subspace. And this case also you have that U content in W, so U minus W is just phi, because U already content in W, so U complement U intersection W complement is phi. So if this is phi, then V minus U minus W is just V. So it is by default this is vector space itself, so it is just trivial subspace. So this is also a subspace. So in either case you get that this U minus V minus W, that is a subspace. So converse this thing is also done. Okay, so for this part, okay, so I'll take a pause if you have any question for this part. So do anyone have any question? Okay, so then let's proceed to this one, and this one actually uses the previous part of this question. So for the time being I'm like skipping, because this is already 6:42. I'll somehow go to the eliminate the system of linear equation part. So okay, so let's go to that question first, and then if I get time, I'll come to this question. Okay, so this is a given linear system of equation where this A is some element of a field of characteristic not equal to 2. That means there 2 is not equal to 0, or 1 plus 1 is not equal to 0. So for that we need to find out A such that this system has exactly one solution, and in general we have to like find the solution of this system of equation. There is three equation. So one example also done in lecture also. Okay, so let us do that. Like there was the unknown was in the right hand side, but here you have unknown A as a coefficient in the left hand side of this variable x1, x2, x3. Okay, so the standard process for this is the Gauss elimination, that is consist of three basic moves or elementary operation on this equation. Okay, so we'll just apply them, and we'll find when this system has solution depending on the value of A. Okay, so this system I first of all recall that for the Gauss elimination, I should first see the first variable, namely in this case say x1, and see where the non-zero coefficient is there. So I'll take that to the first equation. So suppose this is my system, given system epsilon A. Okay, because it is depending on A, so epsilon A. So now I'll apply the like change of the equation, because this x1 has coefficient 1, so I should take that to the first one. So applying epsilon A to just G12. So this is say my G1, this is G2, or so this is G1, G2, G3. Okay, so then this is, I apply G1, interchange G1 and G2. Okay, so this will then become x1 plus x2 minus x3 equal to 0. So this is my new G1, and this is ax1 plus x2 plus x3 equal to, this is 1, and this is x1 plus ax2 plus x3 equal to 1. Now we apply the eliminate this x1 from the below two equation. So again we apply two operation, one from this just new G2 minus a G1, so multiply this by a and then subtract from the second one, and the other one is just G3 minus G1, because here the coefficient is 1 itself. So this is just x1 plus x2 minus x3 equal to 1. This is becomes 0 because ax1 minus x1, that is 0. So other thing is just 1 minus a x2, this is 1 minus of minus a, so this is 1 plus a x2 x3, and this is 1 minus a, right? And here you have again a minus 1 x2, and this is 1 plus 1 minus of minus 1 is in 2, so this is 2x3, so this is equal to 1 minus 1 0, right? Now note that this 1 minus a x2 and this is just a minus 1 x2, so if I add them just, so this will again goes to 0. So without like dividing this by 1 minus a, because I don't know whether a is 1 or not, so I'm just applying another operation G3 minus G2 to like reduce this to a further. So x1 plus x2 minus x3, this still remain 1, and this is 1 minus a x2 plus 1 plus a x3, this is 1 minus a, and this is just 0, and this is 2 plus 1 plus a, so 3 plus a x3, that is 1 minus a. Fine. So now we are like in the least possible case without you putting condition on a. Now see that from the last one, if we have this a equal to minus 3, then a minus 3 minus 3, that this becomes 0, so this is 0 left hand side, and this is 1 minus of minus 3, so this is 4. But being a the field being not equal to characteristic not equal to 2, so that 4 is also not equal to 0. So on one hand you get this is 0 and this is non-zero, so this cannot possible if you have a equal to minus 3. So case 1, if a equal to minus 3, then this modified G3, but I am still writing that as G3. So G3 becomes 3 minus 3 x3 equal to 1 plus 3, so that is 0 equal to 4, which is impossible. As our the field, that means as 4 not equal to 0 in K. So here I use the characteristic thing, that characteristic not equal to 0. Okay, so as this is impossible, so this implies that for a equal to minus 3 the system has no solution. Has no solution if a equal to minus 3. Okay, so next the case we should consider that a not equal to minus 3. Okay, so if a not equal to minus 3, then a might be equal to 1, right? So there is this condition that if a equal to 1, then in this case this is 0 and this is 2x3 equal to 0, so x3 must be 0, because again you use that this 2 not equal to 0 in your field. So I must have this 2 times x3 equal to 0 should imply x3 equal to 0, and here in this case this x2 gets like the coefficient of x2 gets 0. In this case this is 2x3 and this is 0. So in any case these two are compatible and you get that this this thing that x3 equal to 0, and with this condition that x1 plus x2 minus x3 equal to 1. Okay, so so consider the next case then. So case 2 is a not equal to minus 3. So sub case is that a not equal to minus 3, so it can, a might be equal to 1, right? Sub case 1, that a equal to 1, then reduced system become x1 plus x2, so x1 plus x2 minus x3 equal to 1, and this is 0, so this is 2x3 equal to 0 in the both case. In this case also you have like, equal to 1, so 4x3 equal to 0. So 2x3 equal to 0, 4x3 equal to 0. But in any case this x3, so from these two you get x3 equal to 0, as again 2 not equal to 0 or in k, right? So x3 is 0, so this implies that you put x3, so you have that x1 plus x2 equal to 1 and x3 equal to 0. So I can put anything like so. Then the solution set of this of the system when a equal to 1, so this is epsilon 1, this is given by all x1 x2 x3 belongs to k3, k cross k cross k, such that x1 plus x2 equal to 1 and x3 is 0. So this is your solution set. So in particular you can write, you can just write it as like x2 is 1 minus x1, so this is x1 1 minus x1 comma 0, so belongs to k3, that means x1 clearly belongs to k. So this is the solution set. Okay, and okay, so in this case note that this if your field k was infinite, then this set is clearly infinite. Okay, now the remaining subcase that a not equal to 1, a not equal to 1 and not equal to minus 3, so then I can, so subcase 3 is or 2 is a not equal to 1, so a not equal to 1 or minus 3, so then I can reduce the system to further, so this final this system further, because a not equal to minus 3, so I can get this x3 equal to 1 minus a by this 3 plus a, right? So or another thing is that if 1 plus a is again 0, that means a equal to minus 1, then you get 2x2 equal to 2, So again you get to x2 equal to 1, so x2 equal to 1, and in this case x3 becomes, so that is particular. So let's do this one, a not equal to 1, so we can reduce the system further to this one, that x1 plus x2 minus x3 equal to 1, and this I can divide also by 1 minus a, or in particular I can first take x3 equal to 1 minus a by 3 plus a, and this I can take at x2 equal to x2 plus 1 plus a by 1 minus a x3 equal to 1, right? Because I am dividing by 1 minus a is non-zero, so this thing. So from this one you again get that x2 equal to 1 minus 1 plus a by 1 minus a into x3, so 1 minus 1 plus a by 1 minus a into x3 I know this is 1 minus a by 3 plus a, so this is just 1 minus a 1 minus a cancels, so 3 plus a minus 1 minus a minus 1, so this is 3 minus 1 2 by 3 plus a, fine. So this 3 minus a minus 1 minus a, so 3 minus 1 2 by 3 plus a, and x1 is again, so x1 is 1 minus x2 plus x3, so 1 minus x2 is this one 2 by 3 plus a, and x3 is 1 minus, so plus x3 is 1 minus a by 3 plus a, so this is 3 plus a minus, so 3 plus a minus 2 plus 1 minus a get cancelled, so this is just 0, right? 3 plus a or no, sorry, this is just 2 by 3 plus a, so 4 minus 2, so this is just 2 by 3 plus a, so it is just equal to x2 itself. So x1 equal to x2 equal to 2 by 3 plus a, and x3 equal to 1 minus a by 3 plus a, right? So that you get this is like x2 so x1 plus x2 gives 4 by 3 plus a, minus x3 gives you 1 minus 3, so this is 3 minus 3 plus a by 3 plus a, so this is 1, so these are all satisfied, so hence the solution set is x1 equal to, you get x1 equal to x2 equal to 2 by 3 plus a, and x3 equal to 1 minus a by 3 plus a, that is, so in this case L epsilon a equal to just a single point, right? 2 by 3 plus a, 2 by 3 plus a, and this is 1 minus a by 3 plus a. So when a not equal to 1 minus 3, neither equal to 1 or minus 3, even if you get a equal to, so even if you get a equal to 1, in that case also you are getting so this in that case you are getting like infinite solution, so that is not the case. So anyway, so in that case you getting infinite solution there for equal to 1. So these are the all three, so hence L epsilon a, this equal to 3 cases. One is phi if a equal to minus 3. It is infinite set, say x1 1 minus x1 0, such that x1 belongs to k if a equal to 1, and you have the unique solution is 2 by 3 plus a 2 by 3 plus a 1 minus a by 3 plus a, this thing if a not equal to 1 minus 3. So hence the asked question that for which a this system has exactly one solution, you see that in this case you have exactly one solution. So thus for a not equal to 1 or minus 3, so or if you should write in that form, that if a belongs to k minus this 1 comma minus 3, then the system has unique only one solution, has only one solution. Okay, so is this fine? So in the in your assignment you also see this kind of question, so you should solve that like in this form. You should first apply the Gauss elimination, the basic three basic three row operation, and after doing that you will reach in this form. Then you consider the cases whenever you are dividing by something, so that should be non-zero or that has inverse in your field, so use that and you get this condition. Okay, so okay, this is already time. So yes
sir, in the matrices form also we can do this, no?
Matrices form also, it is just you can write this as in this form, na, x fx equal to b, but this a is just your matrix, this a 1 1 1 1 minus 1 1 a 1, this matrix, and your b is just 1 1 1. So in matrix form also we exactly do we apply the Gauss elimination there to make this matrix into row reduced form, and then from that I'm just doing the same thing here, but not writing the matrix but the equation itself.
Got, sir. Got, sir. Got.
Yes. Okay, so any other question?
Sir, can we take a equal to minus 1?
Yeah, a equal to minus 1 is not problem, because you see here the reduced thing, a equal to minus 1 you just get equal to that 2x2 equal to 2. Okay, and in this case a equal to minus 1 gives you 2x3 equal to 2x3 equal to what we get, so 2x3 equal to again 2, right? So x3 and x2 both are equal, so and x1 is also 1, so that solution you will get here, that is unique solution, right? So a equal to just put minus 1, so it is 2 by 2 2 by 2, and this is again 2 by 2. So that you don't have to consider separately. I also thought that you should consider that case, but that case is not needed, that is already included in this case, that whenever a is not equal to 1 or minus 3, because only you need this 3 plus a is invertible, and in this case that 1 minus a, this is you can also invert, because so that you can get this x2 coefficient of x2 is 1, so you only need the invertible of this 1 minus a and 3 plus a. So in our case, in the sub case, we already got there, so that is all, you don't have to consider separately, that is included in this case.
Okay, sir. Thank you.
Okay, so so it already 7:04. Do anyone have any other question related to course, lecture, or anything? Okay, so then I just give it just a little bit of hint for this solution, this problem, that if you have a system of equation in a field K, which this A, I, J, B, I all are belongs to a field K, and that is a subfield of another field L. If in the field in the bigger field, so here K is subfield of L, and in the bigger field if you have a solution of this system, then in the below field also you have a system. That is simply because you can apply the like this Gauss elimination method to this system to reach into some sort of the form that at some lower row these are all 0 and above you have some reduced form, and that reduced form you know that you either have solution or don't have solution. If you have solution, that solution is in k power n, but if there you don't have solution in k power n, then L being just a superset of that, there also you can't have a solution. It's simple due to the just Gauss elimination, that thing. But in this case you are saying in the above field you have already have solution, so you must have a solution in this k power n also, because otherwise that contradicting the previous thing. So the main so hint is the that apply Gauss elimination and to get a reduced system, get a reduced system which has either a solution or not solution, or not in k power n itself. If you don't have a solution in k power n, then you can't have also solution in L power n. But in this case you have a solution in L power n, so you must have solution in k power n. So that's the argument. Just you have to write the argument, nothing mathematical is there. So okay, so that's all for today then. We may discuss this thing. If you have question, just try this one, the similar question we have done in the previous thing, that if this map is injective then k must not be finite, and in this case it is showing that if epsilon is surjective then k has to be finite, otherwise it cannot be surjective. So the similar argument work there here also. So the notes already I have given in the description of YouTube video. So in this video also I'll give the note lecture this notes PDF link there, so check it there. Okay, so this all for today then. We'll meet again next week.